In this lecture, we're going to discuss trace-based compilation. In particular, we're going to overview some basics of JavaScript and then dive into a paper on TraceMonkey. This paper is a PLDI paper from 2009. Andreas Gall is the first author, and there's lots of other authors. And the paper is entitled Trace-Based Just-in-Time Type Specialization for Dynamic Languages. So as we've discussed in previous lectures, there are multiple ways to translate code from high-level source languages or bytecode languages that are architecture independent to native code at some target site where we're executing that code. Code translation in this context is performed online while the program is executing. Our options are interpretation, where we execute, that is, we parse and translate line by line each statement in the program. This means that if there's a loop and I encounter that statement again, I perform the same work repeatedly. We talked extensively about how to optimize interpreters with techniques like direct threading and super instructions and replication. You should be familiar with those optimizations by now. Typically, interpreters are written in low-level languages like C and then compiled. By doing this, we can make the interpreter itself portable. That is, it's easily retargetable to different architectures. And that means our programs become portable if they execute over interpreters that are available for different targets. Interpreters are great for fast prototyping of new language features and instructions, and can be used, like they are in the Ruby language, to define operational semantics for the language. We discussed just-in-time compilation. This is the process of translating an entire method at a time to native code at runtime when you first invoke it. When the program invokes a method for the first time, at that moment it is compiled to native code and then executed. Future invocations of this method are jumped directly to the compiled code for execution. This is called just-in-time compilation. We also discussed dynamic compilation. Dynamic compilation is a more general term than just-in-time compilation. It encompasses just-in-time compilation, but it also allows compilation of methods to happen repeatedly throughout the execution. We may want to recompile a method once we have more information about the behavior of that method over time. The adaptive compilation system of JIKES-RVM that we discussed in class uses a form of dynamic compilation. Dynamic compilation also enables multi-mode compilation, which is exactly what JIKES-RVM does to take advantage of dynamic compilation and to reduce its overhead but achieve its gains. The idea here is we're going to at first interpret or fast compile methods when they're first invoked so that we don't impose a lot of overhead and so that we can increase or decrease the cost of starting up a program. This allows us to sample or profile the program, as we discussed in prior classes, to figure out what's hot or what optimizations might be effective on the code that's executing. Only when we discover where compilation, more advanced compilation, and optimization will pay off do we then apply it. This applying selectively our optimization is referred to as adaptive compilation or adaptive optimization. This is where we recompile methods once we've learned about their behavior and can optimize them accordingly. This way we only apply compilation and optimization effort and therefore overhead when it's going to pay off, or when we believe it's going to pay off, or when it's most likely to pay off. Again, profiling and sampling is key here so that we can identify where the opportunities are for compilation and optimization. One thing we haven't discussed yet is trace-based compilation, and this is the idea of compiling at runtime, but instead of compiling an entire method at once, we're only going to compile portions of methods at once. In particular, we're only going to compile paths that we think are most likely to execute through a method. A path through a method is sometimes called a trace in the paper we discussed today, it's called the trace. We're going to store traces, paths through methods that we compile in a code cache. When traces connect, that is, some traces lead to other traces, when those connections, those traversals between two traces happen frequently, we can link them together into one longer trace. Note also that traces can go across method calls, method boundaries, since they are just a series of instructions. It complicates matters to continue a trace across a method call boundary into another method, but you get the same benefits of inlining when we do. Trace-based compilers are used in lots of places. They're used in binary translators. That's where we wanted to convert one binary to another binary on the fly. And binary instrumenters, where we want to take binary code and instrument it. Systems like PIN and virtualization systems use binary translation and instrumentation, and thus trace-based compilation and translation to achieve their goals. There's also binary optimizers, where we take a binary that exists and try to optimize it on the fly. The systems that do this kind of perform this kind of technique include Dynamo, Sun Studio, Solar, and Adore. VMs, that is, runtime systems and managed runtimes for high-level languages, use trace-based compilation often. For JavaScript, there's Mozilla's SpiderMonkey, which we're talking about today with the paper on TraceMonkey. Spur is also available for JavaScript. There are trace-based compilers for Java and systems called Yeti, HotPath VM, Hotspot TraceJIT, IBM's Testarossa, and Dalvik virtual machines. PyPy performs trace-based optimization and compilation for Python, and LuaJIT does the same for Lua. When we have traces, we have to store them in memory, and we don't know how big they're going to be, and we don't want to store all traces because some traces may no longer be used. So we're going to translate traces and store them into a code cache. In order to translate traces, what we're going to do is produce dynamic basic blocks. You know from prior lectures what static basic blocks are, but in this case, we're going to generate dynamic basic blocks. And these are basic blocks determined by the actual flow of the executing program. Here's an example. On the left, we've produced the static basic blocks for bytecode instructions of a Java method. On the right, we've produced dynamic basic blocks for those same instructions and static basic blocks. So on the left, we identified our leaders, and then our leaders are the first instruction of a method. They are the target of a jump or a conditional branch, and they are the instructions that follow a jump or a branch. Once we find our leaders, we know how to connect our instructions by figuring out where the last instruction of the basic block is going to next. I've left off the edges between basic blocks in this example. You can see the difference between static basic blocks and dynamic basic blocks by looking at the example on the right. In this example, we start executing the program, and we just execute instruction after instruction and write down the instructions as we go. Whenever we hit a conditional branch, we draw a line that ends the basic block we are currently in. The next instruction that we continue with starts the next basic block. I've included the labels from the static basic blocks on the right on the instructions on the left so that you can see where the static basic blocks in some cases would have started. Because we're just simply executing, we have no notion of labels. We're just going to execute blindly until we hit a conditional branch or an unconditional jump. And that's what we're doing here. Notice that we can make the basic blocks on the fly by executing the code this way. However, we have some additional instructions. That is, our basic blocks have some redundancy in them. Namely, we don't start basic blocks at the target of all conditional branches or unconditional jumps in dynamic basic block world. We simply execute until we hit a conditional branch or a jump, and that's where we start our next instruction. If it happens to be at a label, we're lucky, and it maps to that of the static basic blocks. But in some cases, like in basic block 2, the skip label is in the middle of a basic block. We're never going to jump into this basic block in the middle, but I've included the skip just for your reference. Notice that the 3 instructions in skip are repeated down below when we jump to skip during the execution. Basic block 4 repeats instructions that are in basic block 2 because we can't jump into a middle of a basic block because that would violate the definition of what a basic block is: single entry, multiple exit, series of code instructions. So basic blocks, again, in summary, are basic blocks that are generated on the fly as the program executes, and they're not as clean as static basic blocks are, but because we don't have to make multiple passes over the code, they're faster to generate. However, the downside is that they have redundant instructions. That is, instructions are repeated across some basic blocks depending on how the code executes. You should be able to draw static basic blocks and dynamic basic blocks if I tell you the inputs to a program for bytecode instructions. Once we generate our traces, we're going to store them into a code cache. Again, traces are a series of dynamic basic blocks that have a single entry and possible multiple exits. Traces can go across function call boundary, essentially doing the same thing as inlining. This is a nice advantage, although it does complicate matters a little bit because we have to keep track of where our function call boundaries are. We're going to store our traces into a code cache. This is going to be a fixed area of memory of a fixed size, and we're going to fill that up with traces as we discover and compile them. Every time a trace is used, we're going to jump to it in the code cache and execute their native code so it's super fast. In order for the translator, when it encounters a piece of bytecode that has already been translated, it uses a map to figure out if there's a translated trace in the code cache. If it is, it jumps through it. We can also connect traces in the code cache together via links. If there's a block that has a fall-through edge to another block in the cache, if there's a block that is a jump target of one of the ones in the cache, or if there's a block that jumps or falls through to a block already in the cache, we can link these blocks together. In our paper, this is called chaining or stitching. This allows us to avoid jumping back into the interpreter every time we go between the code cache and the interpreter as a source of overhead. Here's an example of what's happening in the system. When we're executing in the interpreter, we're going to execute code, and every time we start a new dynamic basic block, we check to see if that source instruction has a map into the code cache, the target program counter. So that's the virtual program counter is the source instruction, source PC, SPC in the example, and the program counter in the code cache for the native code is called the target program counter or the TPC. We keep a map between SPCs and TPCs to know what we have in the code cache. We interpret checking the map when we hit a new start of a trace. If the trace is already in the code cache, we jump to the code cache on a hit and execute it directly. Code cache entries may have links between them, as shown in the pink dotted line in the bottom right figure. This means that 2 traces have been executed, one right after the other, repeatedly, so much so that they become hot, and therefore we link them. We will only jump to a trace and we'll always put guards on a trace to make sure that the trace is as expected. If we ever are in a trace and we get finished with a trace, we're going to jump back to the emulation manager, which will then help us continue either in the interpreter or with another trace in the code cache. A code cache is different from a memory cache, but they both sit in memory. The key difference is that the code cache has a fixed size. The other key difference is that there's no backing store as in memory caches. We're going to have to keep 2 key code cache operations operating all the time. That is keeping track of the source in the bytecode and the target in the code cache so that we can keep the mapping between them correct, so we can jump back and forth. We're also going to need to be able to come back out of a trace to get to the source instruction, so we keep a map in the reverse direction as well. Because the code cache size is fixed, we have to decide on a replacement policy. That is, what do we do when the cache fills? There's lots of code cache replacement policies that we can use. I'm going to go through some of the most common ones. The first one that comes to mind is least recently used. That is, you want to throw out the trace that has been used further in the past, longest ago, because if it hasn't executed for a while, perhaps it won't be executed for in the future. This is really hard to implement, as it turns out. It's a nice idea, but we're going to have to use some sort of heuristic to make this happen efficiently. When we have traces that are linked together, this gets really complicated because we have to figure out who's linked to who and figure out who to kick out together. It also can lead to fragmentation, holes where nothing will fit in the code cache, just like we discussed in our garbage collection lectures. So we can even back up further and say, hey, let's not do anything complicated first. Let's just do something really dumb and stupid and see if it works. One idea is to flush when full. That is, fill up the cache with traces, and when the cache is full, just flush the whole thing. This may sound silly and stupid to begin with, but it's really simple to implement, and it may do okay in the long run. In fact, what does work really well in the long run is a variation of flush when full. It's called preemptive flush. And this is the idea that we talked about in our profiling lecture when we talked about phases. Programs go through phases. If we can figure out when a new phase is starting, we can flush the cache preemptively. If we can do this, and we don't have to use a ton of intelligence to figure this out, we can do things like when we start to compile new traces quickly, that means we've started executing in a new hot region of the program. We can flush the cache and start filling it up with the new hot regions. This works really effectively and is very simple to implement. We can do other things also that are commonly used in code caches in modern systems. One idea is called fine-grained FIFO. FIFO stands for first in, first out. This is where we keep the code cache, or that is, we manage the code cache as a circular buffer. We fill it up from the top to the bottom. When we reach the bottom, we kick out what's at the top and start filling in again from the top to the bottom, and we keep this circular buffer going. We still have to, and we can do this on a trace-by-trace basis, and that means that's what is referred to as fine-grain. We fill up the code cache by traces, and then we go in, then when we fill the cache, we kick out the first trace that we put into the code cache and replace it with a more recent one. The problem we face when we're using fine-grain anything in a code cache is that we have to worry about the linkages between traces. Linkages are important because it identifies hot paths between traces, but it complicates matters when we want to kick things out, since linked traces may have their pieces be in different parts of the code cache. So one way we can improve over fine-grained FIFO is to use a coarse-grained FIFO. That is, to designate parts of the code cache as big chunks, and we'll fill up each chunk at a time, and we'll fill up the entire cache this way. And then when we wrap around our circular buffer, we'll kick out an entire chunk at a time. And so therefore, we only have to worry about linkages between chunks, not linkages within chunks. So what we're concerned with in today's lecture is an implementation of JavaScript by the folks at Mozilla Corporation and Adobe Corporation and Intel Corporation who are collaborating on this work. So we want to implement a code cache, a trace cache for JavaScript language. However, we need to know a little bit about the JavaScript language, since we haven't talked about it much in the class. It's a dynamic language, much like Python, which we have talked about quite a bit in the class. It runs in an interpreter and typically in a browser, an interpreter in a browser. The runtime is embedded in the browser for most JavaScript implementations. However, it is possible to execute JavaScript outside of a browser in a runtime system. An example of this is the Node.js runtime system. Because JavaScript is dynamic, like Python, all lookups for anything and any name used by your program is done at runtime. Because of dynamic typing, variables have no types, and so everything has to be looked up. We don't know the type of anything statically. All variable accesses have to be looked up at runtime to know how to access those variables. If we have a method call or a field access, for method calls, we have to perform dynamic dispatch in all cases, since we don't know what variables refer to. Similarly, for fields, we have to do the lookup for fields dynamically because we don't know if a field, what the type is of the object that we're referring to, and therefore whether it has the field at all. JavaScript complicates matters because of its implementation of inheritance. I'll speak a bit more about this in the next slide. However, inheritance requires a lookup for every single level of the hierarchy, and this includes lookups that employ local hash tables as well as global hash tables, which complicates matters. Fields and methods in JavaScript can be added dynamically on the fly via a use or a call, and so we never know whether an object is going to have the member or the attribute that we're interested in. So we must perform the we must perform the operation, do the lookup for every operation on the fly so that we don't miss anything. As mentioned in the previous slide, JavaScript's implementation of inheritance uses prototypes. This is different than the classical inheritance where we use classes. If you're interested in the difference between prototype inheritance and classical inheritance, I have a set of related readings in the lecture notes, but the scope of these topics are beyond this class since we don't have much time left. Also, if you're interested in automatic type inference for JavaScript, I include some papers on that in the related readings section of the class. Like all dynamic languages or all object-oriented languages, you have the concept of boxing. Boxing is where we have information embedded in the object itself, usually in its header, to describe the object's type and its layout. Anytime you want to get to the actual data within the object, that is the fields, you have to unbox an object. The other thing about JavaScript is they do have any bytecodes at all, most JavaScript implementations just operate on source. Some JavaScript implementations operate on bytecodes, like the one we're talking about today for SpiderMonkey and TraceMonkey. The bytecodes, however, are still very fat. They're very high level. That is, there's a ton of work going on for each bytecode. If you remember our interpreter paper and our interpreter optimizations, this is like having super instructions in the bytecode. Instead of having lots of fine-grained bytecodes that do a little bit of work, we have a lot of fat bytecodes that do a ton of work. This is similar to Python and Ruby, but very different from Java and G4. Traditional interpreter optimizations that target the dispatch loop, like we discussed in class, will have little impact on such languages like JavaScript, as we showed for Ruby and Python. So today's paper is about trace-based compilation. The TraceMonkey system uses a mixed mode compilation. That is, it uses an interpreter first before it determines where their hot sections of code are. It makes two key assumptions that are different than other work in this area. First, it makes the assumption that most time is spent in hot loops, and therefore it's going to focus its tracing on hot loops only. It also assumes that loops are mostly type stable. That is, through one iteration, the types are similar to the types that are used in another iteration. This means that if we do generate traces for iterations of loops, then we'll be able to reuse them once they're compiled on repeated or subsequent iterations. Traces and trace monkeys are extended basic blocks. They have multiple exits out the side, but they only are single entry. There's no way to get into a trace except through the top. So that means there's no way to get in through the side, which means there's no joins inside each trace. This significantly simplifies optimization. It also assumes that traces go across a function called boundaries. This again makes it a little more complex because you still have to record the stack frames because the interpreter is assuming that you're calling the function. The trace and the trace cache are assuming that we're going to execute the call in line. So keeping those things consistent is more challenging and more complex, but is possible, and you get the benefits of function inlining without performing any other type of inlining analysis. The contributions of the paper are that they only focus on loops, and they identify a way of producing nested trace trees for nested loops. That is, traces that connect for nested loops without generating too much additional code. Because the naive approach, where you trace the inner trace first and then continue to the outer trace, will overflow the code cache because you'll have lots of code duplication for the outer loop for every side exit and every single type. So this is really bad because you're going to fill up your code cache and you're not going to have enough traces to get some benefit from this. So what they do is they show that a new approach to this is just to give up. And once you exit out of the inner trace, you just start tracing the outer trace separately, and then you can link the two via calls if the link and the call between the two turns out to be hot. Also a key contribution is a real implementation that's used in production, and a pretty detailed analysis of a lot of JavaScript benchmarks. One interesting aspect of the paper is that a loop is considered hot when it executes just one more than the first iteration. This state machine shows how TraceMonkey works. We'll start at the top and work to the left before we go to the right. First thing we do is we use the interpreter in a mixed mode setting to interpret the bytecodes. When we traverse a loop edge, which is the start of a loop, we start to monitor the loop. That is, we start to collect profiles about the loop. This is introducing overhead, and therefore this circle around monitor shows that in the symbol key that we're introducing overhead, and we're introducing overhead for profiling. Once we figure out that the loop is hot, we're going to record the trace. This recording of the trace is going to generate an intermediate representation of the trace called LIR, or low-level intermediate representation. Once we record that trace and we reach the loop header, we're going to compile that trace into x86. Later, if we traverse this loop again and that trace is compiled, we'll enter the compiled trace. There is some overhead with doing so because we're going to have to check that the guards are in place. That is, that all of the types and the control flow that we encountered during the monitoring are the same. Once we've determined that the trace is the same as one of the ones that we profiled in the past and thus compiled, we execute the compiled trace. If we continue to iterate through this trace and the types remain stable and the control flow remains stable, then we execute at highly optimized native code speeds. When we exit out, when we're done with we've completed the trace, we'll exit out the trace to check if what exit we're on. If it's a side exit to the same trace, we can repeat this process. If it's a side exit to a trace that doesn't exist, we'll go back to the monitoring and interpreting of the bytecode. Just to give you an example, they have some JavaScript which implements the uh, the algorithm for the sieve of Eratosthenes. Sorry, I can't say that word very well. This is just a snippet of finding primes, computing primes for the first 100 values from 2 forward. Um, all of when the inner loop becomes hot, that is, it's traversed more than once, the LIR down at the bottom is produced. Note that this one line produces this LIR. This LIR is extremely verbose, again, showing you that native code is much bigger than high-level bytecode or JavaScript code. Um, Part of why this code is so big is because of the low-level native instructions, but also because of all of the guards that are needed to verify that the types of our variables stay the same. That is, k holds its same type, and primes holds its same type throughout the execution of this inner loop. Once this inner loop is deemed hot and the trace finishes, then the system compiles that LIR into this x86 set of instructions. And this is, again, much bigger, even though optimizations have been performed. The compiler optimizations that are performed to generate code like this x86 code are ones that we've talked about in class already. They're the traditional optimizations that are used by runtime compilers. These are simplification optimizations, things like constant folding, constant propagation, copy propagation. Strength reduction is the idea where you have a complex operation like multiply that you change into the equivalent with a more efficient operation such as add. There's also floating point and integer emulation that we can do if you don't have a floating point architecture. CSE stands for Common Sub-Expression Elimination, which we discussed in our optimization lecture. We can also do things that take advantage of the fact that we know we're in JavaScript. That is, we know that JavaScript only has the number type, and so we're going to need to do a lot of conversions between double and int, and we can take advantage of this. And then we do dead code elimination, and we eliminate all kinds of redundancies that aren't necessary in the code to try to reduce the code and improve performance. The JavaScript paper discusses a topic called blacklisting, and this is where we're generating an LIR trace on the fly because it's hot, and we find that we consistently, repeatedly don't finish a trace due to some exception handling. Is typically the reason why. If we try to trace something multiple times and we are unable to finish the trace, then we blacklist the trace so we don't constantly waste time tracing something that's not going to finish. The other thing that's interesting about this paper is that the LIR, the intermediate representation, and the optimizing compiler assume an intermediate representation that's based on what's called the static single assignment form, or SSA form. This is a well-known compiler optimization format that's been used for decades in static compilers. It's typically higher overhead and so not used frequently in dynamic compilers. But in this setting where we are optimizing traces, we are able to use SSA form and thus implement optimizations very quickly and in a regular way, very efficiently. So this is a nice contribution of this paper, I believe. A program in SSA form a program is in SSA form if it satisfies the following two properties. That is, each definition, each assignment into a name has a distinct name. This is similar to the idea of using an infinite number of symbolic registers that we discussed in a prior lecture on compiler optimization. Again, for every new variable, we give it a distinct name. Therefore, we're able to keep all of our names separate from each other. And so every name has one def, that is one definition. So if there's multiple defs, then we're going to use distinct names for those definitions. So every definition has a unique name. To make this work, we have to insert a special operation into the instruction stream. Whenever you have a join on the control flow path, you're going to have what's called a phi function. A phi function is where two paths come together at a join, and since we may have definitions of the same variable that are unique on these different paths, we somehow have to join them. The phi function does this join. It's an operation that, when it's executed, does the join to select the correct assignment for depending on which path was taken. In this example, this assigns to x3 the value of x1 if control comes from the left, and the assignment that occurs is from x2 to x3 if control comes from the right. A phi function is simply a marker for the compiler. It's not a real function. It lets the compiler optimize the block without having to worry about different versions coming in. The phi function will be the operation that selects the correct version when the execution actually does occur. After all of the optimizations are performed, the compiler performs register allocation. The register allocation is really similar to the linear scan allocator that we talked about in a previous lecture. The difference is it goes in reverse. In addition, what's different is register allocation is performed concurrently or at the same time with code generation in this compiler. The linear scan for this register allocator goes from the last instruction to the first instruction and is also a greedy algorithm, much like our linear scan allocator in our previous lecture. So by the time we reach an instruction, v3 equals add v1 and v2, we already have v3 in a register, because if we used v3 after this instruction, we would have encountered it on our traversal from the last instruction to the first instruction. So what we have to do at this instruction is allocate v1 and v2 to registers. If we have registers available, we simply do that. If we don't have registers available, we have to spill something. So the heuristic to spill is a little bit different than our register allocator for our linear scan allocation technique from JAGSAR-VM that we discussed. What we do here is we look at the instruction that follows this one, and we look at what values are in registers. And we consider each one of those values in registers for spilling. For each of those values, we look at instructions that come before this instruction, and we identify the one that is the earliest, that is the farthest away in time from this instruction. That is, that we're going to choose the variable to spill that is defined earliest in this method. By doing so, we make sure that we avoid as many conflicts as possible by eliminating a variable that is spilling a variable that has a long live range. We avoid that live range from conflicting with other live ranges of other variables later. So that's our heuristic. So we're going to spill that variable, and that means we're going to insert instructions to write the variable to memory after the first instruction, after its def, and we're going to restore the value from memory right after this current instruction, the instruction that we're currently considering, because the next use is in the instruction that follows. Other issues that the paper points out that I think are interesting and good for you to understand are how it handles calling external functions. It turns out that dynamic languages call external functions using a foreign function interface, or FFI, quite often. Typically, these high-level languages call C functions to get performance out of their languages. And crossing this foreign function interface introduces a lot of optimization challenges when we're trying to compile JavaScript. The other challenges that we face are access to global variables and when exceptions occur. As mentioned previously, when exceptions occur, we abort the trace. Same as for access to global variables, we abort the trace. Same as for access to the call stack, we abort the trace. If we abort the trace quite often, then trace monkey can be rendered, helpless, ineffective. but the authors of this paper find that this occurs very infrequently. And this is something you should note when you're running JavaScript. You should use global variables at a minimum, and you should rarely use exception handling to manipulate control flow. You can use exceptions to catch exceptions when they occur. That's fine, but you shouldn't use exception handling to implement control flow through your program. The findings in the results are quite interesting. They find that a trace monkey doesn't work well for everything, but it does work well when there are hot loops in programs. That is, for 9 of the 26 benchmarks, the trace monkey did better than G8. G8 is a hot method compiler, a runtime compiler that's state of the art and that Google has produced and released as open source. They also compared to an optimized interpreter, similar to the ones that we studied in class. This interpreter is called SFX, and it uses many of the optimizations that we discussed in previous lectures. They don't measure footprint, so we don't know how big the runtime has grown because we're using compilation. But I assume that it's going to be quite big given the difference in size between JavaScript and native code. It just depends on how much they're keeping in their code cache. Here are some of the results. In some cases, the trace compiler performs really well, orders of magnitude better than V8. But in most cases, V8 outperforms the trace monkey. In all cases, all 3 runtime systems outperform the baseline, which is the SpiderMonkey interpreter. Some of these results are more interesting than others, and I encourage you to look deeper, and we'll discuss them deeper in class.